You have homework for me, please. What's an algorithm? A little more than just a set of steps. It's got to be not just a set of steps, a set of precise steps that gets you the outcome you need, right? You have to specify what goes in. You have to know what to do with all the things that go in. And you have to get an answer, hopefully the right one, out. Where'd the word come from? The word algorithm itself has nothing to do with the former president of the United States. I would love to say that's true, but unfortunately, no. But if you give me Ibn Musa'ad algorithm, then the answer is yes. This is actually a person's last name. Muhammad Ibn Musa'ad, Musa al-Khwarizmi. Algorithm. You just mash it up and anglicize it. He wrote in the years 700, 800, he wrote the first book to change math from geometry ideas to procedures. The book was called Al-Yabar et al-Muqabala, the compendious book on completion and balancing. Completion and balancing. Yabar et al-Muqabala. This is the book that would become algebra. Al-Yabar. So algebra is nothing more than a series of precise steps designed to take the numbers you start with, do something, and get the answer you want out. The somethings are completing and reducing. So an algorithm named after al-Khwarizmi is, what are the steps? What do I put in? What do I get out? Find the 8 ball. How'd you do it? I just looked. But that's not what your brain did. You just did it faster than you care to think about. How did you actually look and find the 8 ball?
You look at the first one, check if it's the 8 ball, look at the second one, see if it's the 8 ball. You look at the third one, see if it's the 8 ball, and then the fourth one, if it's the 8 ball.
That is a linear search. Start at one end and look and look and look and look. Does it match this? Does it match this? Does it match? Ah, that one does. But if I'm really doing the linear search, I should go through the whole list. In this case, I got lucky because I got to the one I wanted when I stopped. So if I was like this, I need to keep track in a different fashion, right? So a search algorithm is a method of finding the thing you want. Out of all of these hacky sacks, this is one of my favorites because it depends on whether I'm in a good mood or not. Again, I can give you this set. and simply ask, what's the biggest? And you'll be able to answer me. But now, here is my friend Stupid Robot. Tell him how to find the largest number in this list. He will do exactly what you said and nothing more. So I will play the job of the moist robot. What do I do?
You assign the first, variable to the first number.
What's the variable?
Okay,
A variable.
you make x 13.
Okay,
The first term is x equals x.
I put the first number in a box, which I will label largest, maximum. I take X and I put it in there.
You put the second term in another box, or y equals the second term.
Now what?
Compare them.
Which one is bigger?
13 is.
So that one that's already there is bigger. What do I do with this one?
Get rid of it.
Now what?
Keep the biggest one and keep going.
I'm afraid you're going to have to be more specific than keep going. See the problem? A precise set of instructions. So let me write down what you've told me so far. Then I took the second value and compare it. In this case, you then said throw it out because it's not bigger. So really I have an if statement, right? If, okay, I'm gonna have to assign some letters here. If it's bigger than max, then what do I do? Aha. Stick A into the spot labeled max. And that would be the same as taking the number that's in here, throwing it out, and putting a new number in. Okay. Else? Do nothing. How do I tell it and keep going?
If there's another variable, keep going.
So somehow I need the loop. Now, I am an old fart programmer. So when I learned to do this, I learned to draw pictures. Y'all saw me use a ruler last time, but this is my ruler. A flowcharting template. When I was taught to do this, I was taught to draw a picture. There's my start. Make my first max, whatever the first number in my list is, A1. Then we'll set a counter, it'll start at 2. And it'll ask me, hey, is J is 2, bigger? If it is, swap them. If not, increment the counter. Have we reached the end of the list? Nope, keep going. Eventually, the reason I learned it this way is because there's no definition of which language I'm going to use. What do you want to write this in now? C, Java, Python, R, Rails, Basic. That's what I learned in. The textbook actually gives me something that is kind of C, and they call it pseudocode. So here's my algorithm, my subroutine, and it says my procedure takes in a list of integers, A1 through AN. I give the first one, assign it to the letter max. Again, your variable names can be as long or as short as you want. Here's my loop. Depending on your coding language, you may or may not require an end statement. But I put it there to remind myself that's where my loop is ending. Again, this is a linear operation. It's going to go through the entire list. So given our list, how many times are we going to do the loop? There are 10 items in there. How many times are we going to do the loop? 9. Because we don't do the loop for the first number, we only do the loop for each of those. But my biggest value wasn't the last one. It's 10, 9, 8, 7, right? It's the 7th number. You are smarter than stupid robot boy here. And therefore, you know, oh, the rest of these numbers are small enough, I don't have to keep going. You have a way to get out of the loop quicker. But my computer is dumb and only ever sees 2 numbers at a time. It doesn't know whether or not there are other numbers to compare to what's in maximum until the counter gets done. When I was learning to program, my computer instructor came in with a bag of groceries. On the table in front of him, he put paper plates, forks, knives, spoons, 3 big jars of peanut butter, 3 big jars of jelly, and he said to the first person, you, tell me how to make a peanut butter and jelly sandwich. So, Roman, what's the first thing I do? Make peanut butter and jelly sandwich. Aha! The very first person in my class just said put peanut butter on the bread. He picked up peanut butter, slammed it on a loaf of bread so they can't eat that. You don't get to eat. Stupid robot boy needs really precise instructions, right? So the characteristics shared by all of my algorithms require what are you putting in? What are you getting out? They require precise steps. Now, precision here is the problem. Emily, I was very glad you decided to use the phrase "and keep going." Because as a human being, you expected me to know what to do. Dumb robot boy doesn't understand. Keep going. Way back in my youth, I took a martial arts class. And my instructor routinely would say, no, you're doing a front kick from your knee. Kick from your knee. What the hell does kick from your knee mean? I spent a month trying to figure out how to kick from my knee. It never, ever got any easier. He would come by and he'd go, no, you're still kicking from your foot. Kick from your knee. Go off and work with one of the other students. And I just kept staring at Fred going, what does this mean? Until one day, I kicked from my knee. And lo and behold, that's the best way to describe that. I don't know how to explain it any other than, no, you're kicking with your knee. Your foot just moves where your knee tells it to go. Kick from your knee. Huh? Anybody who's not in a martial arts class, I might as well be speaking in Farsi. It doesn't make any sense. Precision is a matter of familiarity. If you know how to cook and so on, makes perfect sense. This is why, at this point in time, there are no robot prep chefs. Because you can't give them the precise language that you can give to a human being, or the imprecise language that we actually work in. It would be nice if my algorithm actually found the largest number. If at the end of it, I actually came up with a peanut butter sandwich I could eat. If at the end of my kicking experience, I was able to do a proper front kick. The algorithm should be right. It should, at some point, finish. I should be able to finish the job. Say, here, I'm done. Regardless of what you think about the current Department of Government efficiency, efficiency is something we would like to have happen. So making an algorithm be more efficient is seen as a benefit. What's the trade-off for that efficiency? So how do I make an algorithm more effective, efficient, completable, and it should be general. So the algorithm that I give for finding the largest number in a list should work regardless of what those numbers are, regardless of how many there are. If I give you 1,000 numbers, I should still be able to find the largest, following that set of steps, finish it at some point, do it in a reasonably efficient fashion, regardless of how many numbers you gave me. Now, searching algorithms, in this case, we were searching for the largest, could be slightly different. We do keyword searches, right? We look for items in a list. So let's talk about searches. But before I start talking about searches, questions. What questions do you have about what I'm talking about so far? Okay. A search algorithm literally just means find the thing I'm telling you to find out of the pile of things I give you. Like I said earlier, find the 8 ball. We could always do what you suggested, Seth, and just start at one end and go to the other. A linear search. But now I get to ask you a question. If I'm asking you to search for the 8 ball, when do you stop? The algorithm we wrote earlier to find the largest number, when did it stop?
Stop whenever it ran out of terms or elements.
Runs out of the set, right? Then I have to ask a question. What did I get out of that algorithm? Well, we didn't quite decide, did we, Ian? So I returned the number, the largest number in the list. I said, here's the largest number. I could find me the student in the roster named Dave. And then it goes, Dave. Does that help me? I probably want it to spit out where Dave is, right? Where in my list. So I could ask it instead of returning the value, because here I'm looking for something specific, I could ask it to return the location. However, that in and of itself leads me to a potential problem. Where's the student named Dave in this class? There isn't one. So I need an indicator to tell me the element's not on my list. Tell me where in the list the element is, or return an indicator I can spell that it isn't in my list. Now that could be any sort of a thing. You could say stick up an error flag, make the screen blink red, something. Return the value 0. Return the value null. You get to decide what that flag looks like. But a linear search would require me to give you the list of things and the thing I'm looking for. So I need to pass in to this procedure you can name your procedure whatever you like. I've called this one lin search. The thing I'm looking for and a bunch of things. If I am being precise and attempting to write this in a language like C or usually C++, I have to indicate a data type here, right? If I'm searching strings, I should say string. If I'm searching integers, I should say integers. If I'm searching reals or doubles, I should put that in there, right? Booleans, whatever I'm searching for, I should put that here. I'm going to write this as general as you want, so I'm not going to put a type at the moment. But how do I start this?
X equals A1.
I'm not searching for a maximum this time. I'm just searching for X. I want to know if X is between A1 and AN, right? So I just need to start a counter. Let's start a counter. You can call it anything you want. I called it I, like we did in our sums, right? And we'll let I start at 1, and then we'll go, hey, do we have X at that spot? Again, the type of loop you write depends on the type of loop you're familiar with. This is a while loop. How does a while loop work? A while loop keeps going until
I equals X.
until this condition is false. So what am I going to ask? While I'm looking, if no, I don't even need to do an if, because this is going to stop once I find the number, right? So I can just say, oh, what you need to do is you need to step up the counter. Look at the next one. Because if you found it, you'd stop, right? You'd drop out of the loop. I realize I need that to be less than or equal to. I need to look at the last one. If it's strictly less than, then I'll never look at xn. So what happens? It's not the first one. Keep looking. It's not the second one. It's not the, what happens when I find it? This condition is now false. I stop. What do you need to do? Seth? Tell me what I is. But I only do that if I is less than or equal to n.
Is it always gonna be the, because I is one and one is a valid index?
Yes. But if I was 1 and AI was A1 was X, I would have fallen out, right? I would never have done this part. This only happens while this condition is true. So as soon as you find the number, you stop doing this and go to this. If you found it in the first spot, you'd immediately go here, right? But what if you got to the last one and you still hadn't found it? What if my number's not on the list? Where's Dave?
Else. Item's not here. Or else return 0 or null or whatever you'd like.
You return a string, right? Return the string not here. And then give it a print command. Print location. Here, I found it. This is the spot it was in. On the graphing calculator, the print command is display. So you can write programs like this on your graphing calculator. You're still looking at this like you don't like it, Seth. Talk to me.
No, I get it now. It's not the way.
I'm bad at coding. I will be the first person to admit that. I am a mathematician, not a CS person. And I haven't coded since Pascal was the language of the day. My last coding class starts in the year 198. A long time ago, man. I get it. I'm not up on any recent languages. When I had to do stuff in C for my PhD thesis, I outsourced. But this, if I give you the list and it's 16 numbers long, here, I'll give you a list. Here's my list. I could say, find the number 19. And you would say, okay, I is 1. Is 19 here? So increment the counting. Is 19 here? Is 19 here? No, 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 no. Yes, what do? What's my value of I? My value of I is 14. So I spit out 14. You'll notice that as soon as I found the number, I could stop looking. I had a classmate of mine in the programming class I took who said, I want you to write a linear search. The teacher expected him to write something like this. He said, oh, sort the list, maximum the last number. I don't have to do any work, do I? Sort the list descending, the maximum is the first number. He never had to write an actual search. Now this algorithm, if I had 1,000 numbers, could take a lot of steps, couldn't it? It would be nicer if I could write a better algorithm. So here's another search algorithm. Binary search actually works a little differently. It says, cut the list in half. And look at the number that is the end of the low half. Is that your number? If the answer is no, ask if it is bigger or smaller. This requires your list to be sorted like ours is. If it's bigger, look at this side. If it's smaller, look at this side. So you cut the list in half every step. Well, that means if I have 1,000 numbers, I run the loop once and I have 500 numbers. I run the loop once, I have 250 numbers. I get fewer and fewer numbers to look through. Even this would take fewer. Problem. This requires a little more bit of counting behavior. I have not just one counter, I have two counters. Same setup. Because a binary search is using comparisons, these have to be numbers types. You can't binary search on strings unless you use alphabetical ordering for your string sort. I need a left end and a right end.
Can you do this with a string as long as you just wanted to know what was the largest string there, like how many?
Then I could
characters
do
were in
string
there?
size,
Yeah,
right? But then what I'm really doing is I'm converting each string to a number, the string size, and then I'm searching on the size. So it's really a two-step process at that point. I transform the list, then I do the behavior. Okay. This loop works as long as the two numbers I've got are different. First, give me the halfway point. Then look at the spot in the halfway point. If the number I'm looking for is bigger than the halfway point, I want to look at this side, right? So I need to look at the bottom of my list and make the bottom of my list this number. The bottom of my list is I. So I'm going to change I here. The number in this spot was smaller than what I was looking for. So look at the next spot to the right. Otherwise, I don't want to look at this half. I want to look at this half. So I don't move the bottom on my list. I move the top of my list. Eventually, that's going to finish. When you finish, I and J are the same number. So you can ask, hey, you've narrowed it down to this spot. Is that the number I'm looking for? Yes or no? If it is, then that's the location. Otherwise, now I want to be a little pedantic here. So let me go back to the list we just had. And let's trace through this algorithm. I am about to become a debugger. I'm going to debug this algorithm by giving it a set of data and watching what happens at every single step. There are 16 numbers in my list. So I start with I equals 1 and J equals 16. Now I'm about to hit the loop for the very first time. Is that true or false? That's true. So I set M. What is M? M is the floor, 1 plus 16 over 2. What's that value? So now, go to A8. Is 19, because that's the number I'm looking for, is 19 bigger than A8? Okay, wait a minute. 1, 2, 3, 4, 5, 6, 7, 8. This is A8. Is 19 bigger than that? So I becomes M plus 1. True. I is now equal to 9. So I finished this and I say, okay, go back to the while. I equals 9, J equals 16. Time for loop number 2. Is I less than J? Nine is less than 16. Now define M. 9 plus 16 over 2, take the floor. What do you get? Mumble, murmur. 12. So now I need to look at A12, right? What's in the A12 spot? Is 19 bigger than A12? Yes. What do? I change the value of I to what? 13. You see what we're doing? We're tracing our algorithm. We're walking through each step, each and every one. By the way, it's going to take me 5 trips through the loop to finish this process. Fumble. Step 3. Oh, 13 and 16. I go to the 14th spot. A14 is 19. Is 19 bigger than A14? No. So this time, instead of changing I, we change J. So now I have I is 13, J is 14. Nope. They're not the same. Keep going. Hey, 13 is less than 14. 13 plus 14 over 2, take the floor. Say that again. 13 plus 14 over 2 is 13 and a half. The floor is 13. So I go to A13. But A13 was, back to my list. Whoop, wrong list. Which is not the number I want, right? Oops. So that's not right. Keep going. But that means I have to change J again. Now J is 13. Oh, wait a minute. No, 19 is bigger than 13. I change I. I becomes 14. Now I have I and J. They're the same. Stop. I'm not in my loop anymore. Okay. Is A14 the number I want? Yes. Spit out 14. So instead of taking 16 steps to work my way through this entire thing, it took 5. This is a more efficient algorithm in this case. Questions? I do this algorithm visually. When I was taught this, I was literally taught you go to your list and you ask for the halfway point. What are you looking for? I'm looking for 19. Cover that up. Go to the halfway point. What are you looking for? I'm looking for 19. Cover that up. Go to the halfway point. I'm looking for 19. Cover that up. Go to the halfway point. I'm looking for 19. Cover that up. Now I equals J. Is that the number you were looking for? It is. If it wasn't, you'd spit out, not here. A lot of algorithms are named after their visual interpretations. Assorting. Because notice I had to use a sorted list to do this, right? I would like you to put this list in order. Now, if you're a smart human being, you go, those are the numbers 1 through 5. 1, 2, 3, 4, 5, I'm done. If you're a dumb rock, like my computer here, you don't know how to do that. So again, there are many different ways of creating a sort. The two I am most familiar with are bubble sorts and insertion sorts. People, I do insertion sorts alphabetically every single time I grade papers. Because I got to put your names in order to put your grades in the grade book, right? So I got to insert them in the right place. Okay, I've got a name with a B. It goes at the top of the pile. I got a name with an M. It goes down here somewhere. I just insert it into the pile I've already graded at the right spot. So an insertion sort creates a spot in the list. And it starts by saying, oh, start with the first entry. That's sorted. Leave the rest alone. Now look at this number. Is that number bigger than this or smaller than this? Well, since it's smaller, insert a space and then move this number. Insert it into the place where it goes. Now the first two numbers are in order. Go to the next number. Is it smaller than this? Yes. Create a space and then insert that, remove the space. Go to this number. Is it smaller than this? No. Is it smaller than this? No. Is it smaller than this? No. You're back to where you started. Stop. Go to this number. Is it smaller? Is it smaller? I finished my list, I'm out. But your computer is stupid. It doesn't know, hey, I recognize this is already being done, because your computer can't recognize it's a rock. There's another version called the bubble sort. Bubble sort, I can spell too. L-E. Bubble sort works by comparing adjacent elements. I think it works best if you write the numbers vertically, but we can write it horizontally. The bubble sort goes through the whole list one fewer time than the number of things in the list. Since this list only contains 5 things, I'm going to go through the whole list 4 times. The first thing I do is look at the first 2 numbers. Are they in the right order? Then switch them. Look at the next 2 numbers. Are they in the right order? Switch them. Look at the next 2 numbers. Are they in the right order? Leave them alone. Excuse me. Look at the next 2 numbers. Are they in the right order? Leave them alone. The last number in the list is now the largest one. Heavier numbers fall and lighter numbers bubble up past them. So at the end of pass 1, I can say that number is in the right spot. Pass 2 is not going to touch that number. But it's going to ask the same questions. Are those two numbers in the right order? Switch them. Are those two numbers in the right order? Leave them alone. Are those two numbers in the right order? So now I know both of those numbers are the heaviest, and they're in the right order. As a human, I already know I should stop. As a dumb box of rocks, I got to keep going. Pass 3 is now going to check. Are those two in the right order? Then do nothing. Are those two in the right order? Do nothing. Those three are in the right order. I still have one more pass to do. I have to compare these two. But that pass is going to tell me to do nothing. So in spite of the fact that I was technically done way back here, my stupid box of rocks algorithm tells me to keep going until I've built up the numbers from the bottom of the list to be sure I have finished. Best part is that at pass 4, I know those 4 numbers are in the right order. And that means that the first number has to be in the right order. That's why I don't need a fifth pass. There are many different ways to think about designing an algorithm. The way you think about designing an algorithm is called an algorithmic paradigm. Some algorithms are designed to make the best possible, biggest first step. If you pay for cash for any object, pay with cash. For an object that is not an even number of dollars, yes, actually, some people do still carry these funny green things. If you pay cash and your change is not an even dollar amount, you get a bunch of coins back, right? Which is preferable? Me giving you 83 cents in pennies or anything else? So if my goal is to give you the minimum number of coins, that's a paradigm. And that means I should take the biggest possible chunk I can out of the pile of change. I'm going to give you 83 cents. What's the fewest number of coins? How do you get it? I start by saying I need to do as much as I can in quarters, right? 83 minus 25, you have a quarter. That's still not smaller than 25, so do it again. 83 minus 50, that's 33, it's still not smaller, do it again. 83 minus 75 is 8, so I can give you 3 quarters. Now go to the next smallest coin, dime. I have 8 cents, can I give you a dime? Nope. Go to the next coin, that's a nickel, can I do that? What's left? 8 minus 5 is 3. I go to the next coin. So the smallest number of coins I need to give you in our current denomination is 8. This is a greedy algorithm because it takes the largest chunk it can first. If you have a coin system that's 50-cent coins, you'd start there, right? You're dealing in euros, they don't do quarters. 50, 20, 10, 5, and 1. Different coin system. The change-making algorithm as a greedy algorithm is in our textbook on page 210. It's labeled the cashier's algorithm. It's an example of a greedy algorithm. But this type of paradigm isn't always going to give you the most efficient algorithm. How many of you have ever had these stupid shipping companies send you a SD card in a box 2 foot square? You order something off of Amazon, it's this big, it comes in a box the size of your head. Why?
Said you can't fit in there, and it said yes, so you can.
It's the box I have at my station, it's the smallest box I have that fits it. Put it in the box. Period. It's more efficient for me to send that giant box than it is for me to go down the line looking for a smaller box. That's called a bin packing algorithm. And again, the bin packing algorithm is a greedy algorithm. There are variants on the bin packing algorithm. Each algorithm itself can be decided, is this greedy or not? Then, what are the trade-offs and benefits? One of the biggest problems in computer science right now is if I give you an algorithm, how good is it? Does it actually finish? So there's something called the halting problem. And that's part of what we'll talk about on Friday, but the explanation of the halting problem is in this section. So I will see you all then. Hope you have a wonderful rest of your day. I almost brought the peanut butter sandwich stuff to class.